All right, so we're going to go to a synthesis problem. We're going to use what we just learned from the previous video or maybe the previous two videos and apply to this type of problem. This is like the whole goal. We teach organic chemistry just for synthesis reaction, actually. Try to like help teach you how to think critically. Okay. All right. Synthesis problem. What you're gonna do? You're gonna determine the mechanism first. Does it go SN1 or SN2, and then you predict the product. Right. If you know the mechanism, you should be able to predict the product there. All right. Start with this guy. Look at one thing at a time. All right. One thing at a time. Don't look at the overall reaction. You get confused. Look at one thing at a time. I usually start with an alkyl halide right there. What type of alkyl halide is that? That's the secondary alkyl halide. You should know that a secondary alkyl halide can go either way, an SN1 or an SN2. All right. Now, tiebreaker. Look at the nucleophile, weak or strong. You should be able to tell that hydroxide right here is a strong nucleophile, and a strong nucleophile favors an SN2 reaction. All right. And if you look at the DMSO, the solvent, dimethyl sulfoxide, is also a type of a product solvent facilitating SN2 reaction because it leaves the nucleophile alone. All right. So the first reaction here is going to go on SN2. And if this were to go on SN2, the mechanism is backside attack. Hydroxide going to go attack that carbon. And you're going to get OH on a wet line. That's how you do it. Determine the mechanism and then the product. All right. All right. Try to do that on your own and then check with me every single one of them. All right. Now go to number 2. So also secondary. So totally SN1 or SN2 either way. If you look at methanol, you should know that's the weak or strong. A weak nucleophile. No charge. Oxygen is small. Low polarizability. All right. So this is going to be an SN1 reaction. So this favor SN2. And no solvent there, which means that methanol going to act as a solvent as well. Also, a polar product solvent can stabilize everything. Good for an SN1 reaction, stabilize the carbocation. And so this reaction is going to go in SN1. All right. And this were to go in SN1, the reaction is going to pass through carbocation. So watch out, racemization there. All right. If you remember, if you see carbocation, 2R events, racemization and rearrangement, you're going to watch out there. Right, you should get these two diastereomers. They are not an enantiomers, right? They are not an enantiomer. They are diastereomer because the stereochemistry of this carbon and that carbon doesn't change. You see that? Doesn't change. Only change is just this, up and down. If this were to be an enantiomer, the enantiomer of this compound is down and down, like a dash line and dash line. But you don't get that. This is diastereomers. All right. Okay. All right. Next one. This carbon right here. What we got? Secondary can go either way, SN1 and SN2. All right. Now hydroxide. That's a strong nucleophile. Talk about right here in the top right here. So strong. We're gonna go SN2 for sure. If there's were to be an SN2 backside attack, you will get an OH on a dashed line. All right. All right, next one down here. All right, same alkyl halide SN1 and SN2 works for this guy. All right, if you look at water, water is the weak nucleophile. Right, no charge there. It's a weak nucleophile. It's going to be an SN1 and can also act as a solvent, which is a polar product solvent, also SN1 as well. So the mechanism going to be an SN1 mechanism. If this were to be an SN1, you get carbocation right here. Right. So you should get the water can attack from the front and the back. You get enantiomer there, right? You get a racemization there. Okay, so two products. They are enantiomers. All right, next one. What we got right here. So this carbon here is secondary carbocation. All right, so you can go either way, SN1 or SN2. The nucleophile, weak or strong? Ethanol. Oxygen with 2 bonds, no charge, just like a water. This guy are weak go SN1 reaction, but this favor SN2. Ethanol can also act as a solvent. It's a polar product solvent, so favor SN1. So the whole reaction go SN1. All right. All right, let's see what happens. So if it's were to go on SN1, bromine leaves, you get carbocation right there. Ethanol can attack from the front and the back. You get a diastereomers. Okay, so 2 diastereomers. Anything else could happen though? Well, watch out though when you see a carbocation. Right? When you see a carbocation, there are two R events that could happen: rearrangement and racemization. This is racemization. This is racemization. Yeah. Now, what about rearrangement though? Can you do rearrangement? Well, when bromine leaves, you get a carbocation right there. All right. Secondary carbocation is good, but can you make it better? Look around. Start with the hydride shift. You see hydrogen right there. Move it, hydride shift. You get tertiary. So this could happen, right? What about on the left side? Oh, the left side doesn't have hydrogen. You cannot do hydride. Some of you may ask, can I do a methyl shift there, an alkyl shift? Well, you can, but if it's a hydride is much faster. We talk about 1,000 times faster than a methyl shift, right? So hydride gonna take that carbocation, so we go just that, all right? And then in this case, so we got carbocation, and ethanol can attack from the front and the back. You should get one compound plus its enantiomers there, okay? So you should get 4 products total there, like 4 products total, all right? So we have 2 diastereomers and 2 enantiomers in here. All right. If you look back to the 2 SN1 reaction up the top, we already passed through that. They can also do rearrangement as well. All right. I didn't want to bombard you with the rearrangement at the beginning, but yes, those 2 can form a rearrangement when you form carbocation, and you could get to 1 or 2 more products there too. Okay, there's a possibility. We don't know what's going to happen. If you really want to know, you have to do the reaction. Right, if it go rearrangement or not rearrangement, right? So that's gonna be experiment now. But this one we just predict, right? This reaction can do rearrangement. The top 2 up there, SN1 reaction, can also do rearrangement as well. All right. All right. Next one. What we got? We got 2 nucleophilic center there. See that? Secondary can go either way, SN1 and SN2. But this carbon also can go SN1 and SN2, but well, we don't know. Go further, so we can't really tell anything there. But what we know is bromine is the better leaving group, and if this guy's a better leaving group, the reaction center is likely to be on that carbon, not the carbon with the chlorine. Okay. All right. Next one. So look at this guy. Strong or weak nucleophile. That is an ionic bond. So oxygen got a negative charge there. All right. So this got SN2. Look at the solvent. It's going to be an SN2. There's a polar product solvent facilitate an SN2 reaction. So the whole thing here go SN2. All right. Now SN2. So we have negative charge on oxygen. So oxygen going to go to the carbon that can proceed faster. All right. So bromine leave faster than chlorine. So we go attack that carbon. All right. And this is an SN2. So inversion of configuration from a dash to wedge. All right, backside attack. The next one, all right, we have 2 reaction centers. See that? Both are secondary, can go either one SN1 or SN2. But what could happen though? Well, it depends on SN1 or SN2. If it were to be an SN2, this carbon right here have wide open, right? This carbon right here is too sterically hindered there. If this were to be an SN2, should go this one. But if this were to be an SN1, maybe this guy have a rearrangement with a methyl shift. You might get a good carbocation there. Depends. Let's look at the nucleophile, shall we? The nucleophile, we have sodium methyl sulfide. All right. Ionic bond right there. So this is going to be a strong nucleophile going SN2. Dimethylformamide, that's a type of polar product solvent, facilitate an SN2 reaction. So totally this reaction will go on SN2. All right. All right. So if this were to be an SN2, backside attack at the less sterically hindered reaction center. So right there, this guy right there, right? This guy too hindered there, right? So sulfide gonna go attack right there, and you should get sulfur on a dash line. Okay. All right. I hope that this should help you a little. All right. Practice some more because there's a lot of thinking going on here. But be familiar with it, and this will come easier as you practice. Okay.